Welcome to the deep dive. Ever feel like you're just drowning in information, wishing someone could, just boil it all down to the really crucial, mind-blowing stuff? Well, that's exactly what we're aiming to do today. We've got a stack of sources here, articles, research, real-world insights, and we're going to unpack a concept that's, honestly, fundamental to almost every bit of tech you use: vertical scaling. Think of this as your shortcut to getting properly informed. We want to give you those aha moments without that feeling of information overload you sometimes get with complex tech topics. Our mission today: to explore how making a single machine vastly more powerful can unlock just incredible performance, simplify operations like you wouldn't believe, and even tackle critical compliance needs. Get ready, because your whole understanding of scaling, it might just get fundamentally transformed. Okay, let's get into this. We hear scaling thrown around all the time in tech, right? And usually people mean adding more servers, spreading things out, scaling out. But vertical scaling, that's different, isn't it? How would you define it, at its core? What really sets it apart?
That's a great starting point, and yeah, it's a crucial distinction. Vertical scaling, or you'll often hear it called scaling up, it's fundamentally about boosting the resources of individual servers or machines. So instead of spreading the work across lots of systems, that's horizontal scaling, scaling out, you're actually concentrating more power within the boundaries of one existing system. It's all about enhancing a single machine's capabilities to handle a much bigger load, turning it into a real workhorse.
A workhorse. Okay,
Right.
so the core idea is concentration.
Exactly. Resource concentration. That's the key principle. You're literally adding more CPU cores, beefing up the RAM, expanding the storage capacity, or maybe putting in faster processing units, all directly into that one server. The whole goal is to make that single machine incredibly potent so it can manage a much heavier workload all by itself.
And how does that work in practice? What are the different ways you actually scale up?
Right, so there are a few main ways. First, you've got CPU scaling. That could mean upgrading to a processor with a higher clock speed, or one with more cores, or maybe moving to a more advanced chip architecture altogether. Basically anything that lets that single system handle more calculations or more tasks at the same time. Then there's memory scaling. This is a big one. Increasing the RAM capacity. Why? Because it lets applications keep much larger chunks of data right there in active memory.
So faster access, less waiting for storage.
Precisely. Accessing data in RAM is lightning fast compared to pulling it from even a fast disk. It reduces that dependency on slower storage, which is often, the main bottleneck slowing things down.
Makes sense. And storage itself.
Yep, storage scaling. That could be upgrading to way faster technologies like NVMe, SSDs. These things are incredibly quick compared to older drives. Or it might just be about increasing the total amount of storage space available on that one machine.
NVMe. That's not just a faster hard drive, is it? It's got to get a different connection.
Exactly. NVMe, non-volatile memory express, uses the PCIe bus, the same fast lanes your graphics card uses, to talk directly to the CPU. It cuts out a lot of the old overhead you had with SATA drives. Massive difference in speed and latency, especially for stuff that hits the disk hard.
Got it. So CPU, memory, storage, boosting the core components.
Yeah.
But you mentioned modern implementations. It's not just about physical hardware swaps anymore, is it?
Yeah.
Especially with the cloud.
That's right. The cloud and even container technology have really changed the game here. On cloud platforms, you have what's called dynamic vertical scaling, usually through instance resizing. This means you can literally change the CPU, RAM, or other resources allocated to your virtual machine, often on the fly without physically touching anything. Sometimes even without a reboot. It makes scaling up incredibly flexible.
Wow. Okay. So you can just dial up the power when you need it.
Pretty much. And then in the world of containers, systems like Kubernetes have features like vertical pod autoscaling, or VPA. Think of VPA as like an intelligent agent watching your running containers. It sees how much CPU and memory they're actually using, and it can automatically adjust their allocated resources up or down to match. All without you needing to manually intervene. It brings vertical scaling right into these modern dynamic application setups.
So if I'm getting this right, it's like taking one really high-performance sports car, and instead of buying a whole bunch of regular cars, you're giving that one car an even bigger engine, maybe bigger fuel tanks, better tires, just optimizing that single powerful unit to its absolute peak.
That's a perfect analogy. You're spot on. It's about maxing out the potential of one thing.
But this idea, enhancing one machine, it feels kind of old school in a way. It's not something that just popped up with the cloud, right? It must have a history.
Oh, absolutely not new. It has incredibly deep roots, honestly reflecting the entire history of computing. You hit the nail on the head there. Think way back to the early mainframes, mid-20th century. These were the absolute epitome of vertical scaling. Huge machines, immense computational power, all concentrated in a single specialized unit.
Right, because they didn't really network them like we do now.
Exactly. If you needed more power, you generally had to make that machine more powerful. They really set the stage for thinking about performance improvement through enhancing an individual system. Then, fast forward to the personal computer revolution, the 80s and 90s. This is where vertical scaling became something everyday people understood.
Yeah, I remember upgrading RAM, buying a faster processor.
We all do. Putting in a bigger hard drive, that was vertical scaling. It made the whole concept incredibly intuitive. Need more speed, upgrade your PC's components. It felt like the natural way to improve performance for millions. Then, in the enterprise world, around the 2000s, we saw these incredibly powerful multi-core processors arrive, along with much more advanced memory. This fueled huge vertical scaling for critical systems. Think big database servers, core application servers. They could handle massive loads on single machines, and virtualization gave it another huge boost. Technologies like VMware, Hyper-V, they let you run multiple virtual machines on one powerful physical server, so you could really leverage that vertically scaled hardware efficiently, sharing those beefed up resources.
Okay, so virtualization helps share the power of one big machine.
Precisely. And then came the cloud computing era, which really transformed vertical scaling again. It shifted from being purely about physical hardware you managed yourself to being a service. Cloud providers introduced elastic instance resizing. Suddenly, anyone could access incredibly powerful single-system resources. With just a few clicks, no hardware management needed, it democratized scaling up, making it dynamic and accessible like never before.
Okay, so it's got this rich history from mainframes to PCs to the cloud. It's clearly not just a relic. But why the renewed focus now, with all the buzz around distributed systems and scaling out? What makes scaling up so critical today?
That's a really pertinent question. And you're right, there's a definite resurgence driven by some key trends where vertical scaling just fits perfectly. One of the biggest drivers, artificial intelligence and machine learning, AI and ML workloads. These often demand absolutely massive amounts of computation, but critically, they often need it concentrated.
Concentrated, how so?
Think about training a big AI model. You often use GPUs, right? Graphics processing units. These things chew through parallel tasks, but they work best when they have very fast access to huge amounts of data sitting right there in memory on the same machine. Same for high memory analytics platforms. They thrive on what we call unified memory architectures and these super high bandwidth connections within a single system. Trying to spread that kind of workload across many slower network machines often introduces bottlenecks that kill performance. So vertical scaling with powerful GPUs and lots of RAM is often the answer.
Okay, that makes sense for AI. Right. What else?
Regulatory compliance. This is huge in certain sectors. Think healthcare, finance, government. They have incredibly strict rule about data governance, privacy, and security. Vertical scaling helps significantly here because keeping the data processing concentrated within a single system boundary simplifies proving compliance. It maintains data locality, keeping data in a specific place, which is crucial for rules like ISO 27001, IPA, SOX, PCI DSS. Auditing is simpler, access control is easier to manage. It reduces the compliance headache compared to tracking data across dozens or hundreds of nodes.
Ah, interesting. So keeping it all in one box makes it easier to secure and audit.
Exactly. Less places for things to go wrong or data to leak. And another area is edge computing and the Internet of Things, IoT. As we get more devices out there generating data sensors, cameras, smart devices, they often need to process that data locally, quickly, without sending everything back to a central cloud. Think real-time analytics at the edge.
Right, reduces latency.
Precisely. And it saves bandwidth. So these edge devices themselves often need significant local processing power. A great example people might know is Tesla's autopilot system. Those cars have powerful onboard computers. That's vertically scaled hardware right there, processing sensor data locally in real time to make driving decisions instantly. They can't wait for a round trip to the cloud.
Wow. Okay. Didn't think of it that way, but yeah, that's vertical scaling in action.
It is. And even in the container world, things are evolving. Kubernetes, for example, recently introduced in-place pod vertical scaling in version 1.27. This is actually a big deal. Before, if you wanted to give a running container more CPU or memory, you usually had to stop it and restart it with the new limits. Caused a blip in service.
Right, a disruption.
Exactly. But in-place scaling lets Kubernetes adjust those resources for running containers without restarting them. It removes a major operational pain point and makes vertical scaling much more attractive even for these dynamic containerized applications.
That's incredible. So it's powering everything from self-driving cars, ensuring our medical data stays safe, running massive AI models, and even getting smoother in container setups. It's doing way more heavy lifting than most people probably realize. What does this actually mean for businesses? Can you point to concrete examples, real success stories or performance numbers that show the impact?
Oh, absolutely. The impact isn't just theoretical, it's very real and measurable across tons of industries. It translates directly to business value. Generally, industry research shows typical vertical scaling projects achieve somewhere between 50% and 200% performance improvements. That range depends heavily on the specific workload, of course, but those are significant numbers. That's not just tweaking, it's often transformative.
50 to 200%.
Wow.
Okay, give me some examples.
Okay, take e-commerce platforms. We've seen case studies where vertical scaling led to 40% faster transaction processing. And during crunch times, like big sales events, they saw 30% faster page load times.
And that means more sales, right?
Yeah.
Fewer people abandoning carts.
Directly. Better customer experience. Higher conversion rates. More revenue. It's a clear line. Another one. Online gaming. Providers have reported 50% improvements in latency by scaling up their game servers.
Huge for gamers, less lag.
Critical! Smoother gameplay, more responsive interaction, and that led to, in some cases, 20% increases in user engagement. People play longer, stay subscribed. Again, direct business impact. How about financial services? Analytics platforms chewing through millions of transactions. They've seen 70% reductions in batch processing times.
70%. That means faster insights, better trading decisions.
Exactly. Faster fraud detection, quicker market analysis, a massive competitive edge when time is literally money. Even healthcare, patient management systems.
Right.
Reports of 60% reductions in wait times for retrieving patient info. That boosts efficiency for doctors and nurses, but also improves the patient experience. Less waiting, faster care.
Okay, those are compelling numbers across different fields. What about the really big players? Do giants like Netflix or Google use this? I always imagine them as pure horizontal scaling.
They definitely use horizontal scaling for massive global reach, no doubt. But they often use hybrid approaches, relying on vertical scaling for specific critical components.
Yeah.
Take Netflix. Their system architecture actually scales individual microservices vertically based on real-time demand. Like maybe their recommendation engine needs a temporary CPU and memory boost when a hot new show drops. They scale that service up.
Targeted scaling up.
Exactly. And YouTube. Think about all the videos uploaded every second. Their video transcoding servers, the ones that convert videos into all the different formats and resolutions, benefit hugely from vertical scaling. They use powerful machines, often packed with GPUs and lots of memory, to process many video streams in parallel on a single box. It's efficient.
Wow. Okay. Those numbers are seriously impressive. 70% faster processing, 50% lower latency. It's undeniable that this delivers real business value. It's clearly way more than just a technical preference. So beyond these specific applications, what's the bigger picture? What does the market for vertical scaling solutions actually look like? Is this a small niche or a major industry force?
Oh, it's definitely not a niche. The market landscape for vertical scaling is, well, it's booming. It's experiencing really robust growth, which underlines just how strategically important it's become. Get this. The vertical market software sector software, tailored for specific industries, which often relies heavily on vertically scaled performance, was valued around USD 172 billion in 2025.
172 billion. Okay, that's already huge.
Right, but the projection, it's expected to hit nearly USD 579 billion by 2035. That's a compound annual growth rate, CAGR, of almost 13%.
Wow, nearly $600 billion by 2035. That's enormous, bigger than the economy of many countries.
It really is. It just shows how vital this approach is, especially for specialized tasks and industries with tough compliance rules.
Yeah.
Businesses are seriously investing in this, and a lot of this growth is driven by cloud adoption. Research suggests we'll see something like a 121% increase in adoption of vertical industry cloud solutions just within U.S. small and medium businesses.
So smaller companies are jumping on this too via the cloud.
Absolutely. Cloud providers like AWS, Azure, Google Cloud, they're all pouring resources into making vertical scaling easier and more powerful. Better instance resizing, more automation, making it accessible to everyone, not just large enterprises. And even in traditional enterprise data centers, things are changing. We're seeing a shift towards high-density computing, What that means is power requirements per rack are skyrocketing from maybe 4 or 5 kilowatts historically to over 20 kilowatts per rack now in many places.
20 kilowatts. That's a lot of power in one cabinet.
It is, and it directly reflects the power of modern servers designed for vertical scaling, packing way more CPU, RAM, and storage into the same physical space. It's about density and efficiency. And interestingly, from a business strategy angle, studies show that focusing on verticalization, providing the specialized solutions, has a 10-20% positive correlation with year-over-year revenue growth for B2B software companies. Businesses that specialize in this tend to grow faster.
So it's a massive, rapidly growing market, pushing close to $600 billion projected, and it's even linked to faster company growth.
Staggering. Okay, I see why businesses are paying attention, but let's shift gears a bit. Let's get into the how, the technical nitty-gritty. How does this resource concentration actually work under the hood? What are the core principles and the components making it happen?
Right, let's dive in. The magic really happens because concentrating resources within one system offers fundamental technical advantages. The core principle is optimizing within those existing system boundaries. This inherently reduces network latency. Components inside the same box talk over incredibly fast internal buses, not a relatively slow network. Milliseconds saved there can be huge.
No network lag between core parts. Exactly. It also massively simplifies data consistency. If all the critical data lives on one system, you avoid the nightmare of keeping data synchronized across multiple distributed copies. That's a major source of complexity and bugs in distributed systems. And related to that, you eliminate internode communication overhead. Systems don't waste time sending messages back and forth. They can access shared resources directly and quickly.
So faster communication, simpler data management. What else?
A key concept is the unified resource model. Because everything CPU, memory, storage is within that single boundary, applications can leverage things like shared memory architectures and optimized instruction pipelines in ways that are just impossible when things are spread out. For instance, many modern high-end servers use NUMEME, non-uniform memory access.
Okay, what's that?
Basically, it means memory is physically closer to some CPU cores than others. UMA-aware operating systems and applications can make sure a process running on a specific core primarily uses the memory closest to it. This minimizes memory access time, even in systems with tons of cores and terabytes of RAM. It helps these big single systems perform efficiently at scale.
So it helps manage memory access efficiently, even on massive machines. Clever.
Very clever. And then you have resource elasticity, especially in cloud and containers. Things like live migration in the cloud let you move a running virtual machine to different underlying hardware, maybe more powerful hardware without downtime. It makes scaling up seamless.
So you can resize without interruption.
Often, yes.
Yeah.
And in containers, as we mentioned, dynamic resource limits and QS settings let you fine-tune CPU and memory for running workloads on the fly. It's all about maximizing resource utilization efficiently within that single system. CAFD optimization, memory bandwidth, CPU affinity, these become critical tuning points.
Okay, so those are the principles. What about the actual hardware? What kind of components are we talking about here?
We're talking serious hardware. State-of-the-art multi-core processors. Intel's latest server chips, for instance, can pack up to 56 cores per socket, and you can build systems supporting over 4 terabytes of RAM. Just imagine that in a single machine.
4 terabytes of RAM. That's immense.
It's staggering. And you pair that with high-capacity memory modules and critically ultra-fast storage. Those NVMe storage arrays we talked about, they can deliver 10x to 100x the performance of older SATA SSDs. Absolutely essential for feeding those powerful CPUs with data quickly.
So beastly CPUs, massive RAM, super fast storage. What about the software layers managing all this?
Right. Above the hardware, you have crucial virtualization layers. Hypervisors like VMware vSphere or Microsoft Hyper-V act like traffic cops for resources. They use sophisticated scheduling algorithms to distribute the underlying hardware power fairly and efficiently among all the virtual machines running on the system.
They manage the sharing.
Exactly. And in the container orchestration world, tools like Kubernetes VPA are constantly analyzing usage and automatically tweaking CPU and memory for containers, using recommendation engines and controllers to optimize resource use without manual effort. And for really specialized stuff like high-performance computing, HPC, you see architectures combining powerful CPUs with GPU accelerators. Think NVIDIA's A100 or H100 GPUs, each with potentially up to 80 gigabits of its own ultra-fast memory. These are built for massive parallel processing tasks like AI model training or complex scientific simulations. There are even emerging things like storage class memory. Intel Optane was an example that kind of blurred the line between RAM and storage, offering near RAM speeds, but the data persists when the power is off. It opens up new possibilities for vertical scaling architectures.
Wow, that's a serious amount of power. From the cores, to the memory, to the storage, all orchestrated by smart software. It's definitely not just about buying a bigger box, it's about the sophisticated tech inside and how it's managed. So, practically speaking, how do organizations actually do this? How do they implement vertical scaling successfully, moving from theory to a high-performing reality?
Right. Implementation isn't just plug and play, especially for complex systems. It needs a systematic approach. It always starts with a thorough assessment phase. You need to really analyze your current resource usage, pinpoint where the bottlenecks are right now, and clearly understand your future capacity needs. What exactly needs to be faster? How much faster? Tools like AWS CloudWatch, Azure Monitor, Prometheus, they are essential for gathering this data. You need that baseline.
So measure twice, cut once, basically.
It's exactly.
Perfect.
Good analogy. You spend significant time here, maybe 20-30% of the effort, just understanding the problem before you jump to solutions. Then the actual implementation approach varies. If you're on premises, it means physical hardware upgrades, swapping CPUs, adding RAM sticks, installing faster NVM drives. In data centers, it might involve moving to those high-density racks we talked about, which also means thinking about power and cooling upgrades. If you're cloud-based, it's often much simpler operationally. Cloud providers like AWS or Azure offer seamless instance resizing. You go into the console and use an API call, select a bigger instance type with more CPU or RAM, and click Apply. The platform handles the underlying changes, often very quickly.
Much more flexible.
Hugely flexible, great for reacting to changing demand. For container-based systems like Kubernetes, implementation involves setting resource requests and limits correctly for your containers, configuring auto-scaling policies like using VPA, and having good monitoring in place to see how it's working. The key is leveraging the orchestration platform's features. And for databases, which are often prime candidates for vertical scaling, implementation focuses heavily on memory and storage. Tuning things like the database buffer pool, how much data it keeps in RAM, optimizing connection handling, and ensuring it can fully utilize large memory configurations are key to getting that massive performance boost for queries and transactions.
Okay, so different approaches depending on the environment. What about the tools to manage all this?
Yeah, a whole ecosystem of tools exists. For monitoring, you've got platforms like Datadog, New Relic, Splunk. They offer deep insights into resource utilization, help with capacity planning, and can even suggest scaling actions. Cloud providers have their native tools like AWS Autoscaling or Azure VM Scale Sets, which automate the process based on metrics. Virtualization platforms like VMware vCenter have tools like DRS, Distributed Resource Scheduler, that can automate resource balancing and trigger scaling. Kubernetes has VPA. For HPC, you have specialized job schedulers like SLURM and GPU monitoring tools like NVIDIA's DCGM. And databases have their own tools like Oracle Enterprise Manager or specific tuning utilities like PG Balancer for PostgreSQL connection pooling. You need the right tools for the job.
Right, specialized tools for specialized tasks. And how do you know if it worked? How do you measure success?
You measure it with clear performance metrics tied back to what actually matters for the application and the business. Key indicators are things like throughput improvements, how many more transactions per second can it handle, response time reductions, how much faster are user requests served, and resource utilization efficiency. Are you actually using the powerful hardware you paid for effectively, or is it sitting idle? We talked about those 50-200% performance gains. That's what you aim for and measure. You look at CPU metrics like utilization and instructions per second, memory metrics like bandwidth and cache hit rates, especially important for immune systems, storage metrics like IOPS and latency. Did that NVMe upgrade deliver the expected speed up? And ultimately, you tie it to application-specific metrics, database transaction rates, web page load times, batch job completion times. For something like a financial trading system, success might be measured in shaving off microseconds of latency. That's the tangible business value.
Okay, so vertical scaling clearly packs a punch. Immense power, often simpler operations, really impressive performance gains possible across the board. But, in tech, there's always a catch, right?
Mm-hmm.
No silver bullets. What are the trade-offs here? Where does scaling up start to hit its limits or introduce downsides?
You're absolutely right. It's always a balancing act. Understanding both the strengths and the weaknesses is crucial for making the right call. Let's quickly recap the key advantages because they're compelling. Number one, simplicity. That single system architecture just eliminates a whole class of problems you face with distributed systems, network partitions, complex data consistency protocols, distributed debugging. It's often much simpler to manage. Organizations often see 50–75% less operational complexity. That's huge.
Less complexity, easier management. Got it.
Number 2, performance. For certain workloads, especially those sensitive to latency or needing shared memory, the performance can be superior. No network hops, optimized cache usage. Databases, in particular, often fly on vertically scaled systems. And number 3, implementation speed. Swapping hardware or resizing a cloud instance often takes hours. Building out, configuring, and testing a new distributed cluster can take days or weeks. It's often faster to get that initial capacity boost.
Simplicity, performance, speed. Okay, sounds great. Now for the catch. What are the limitations?
Right, the inherent limitations. First, obvious one, hardware constraints. There's a physical limit to how big you can build a single machine. While modern servers are incredible, you eventually hit a wall. Practical limits often hover around 1 to 2 terabytes of RAM and maybe 100 or so CPU cores before things get exponentially more complex and expensive. There's a ceiling, which leads directly to the second limitation. Cost escalation. That high-end hardware, it gets really expensive really fast. The cost curve isn't linear, it's often exponential at the top end. Doubling performance might quadruple the cost. You hit a point where scaling up further just isn't economical compared to scaling out with cheaper commodity hardware.
Okay, so physical limits and skyrocketing costs at the high end. What else?
The big one. Single point of failure. This is the classic Achilles heel. When you concentrate everything on a one powerful system, if that system goes down, hardware failure, software bug, power outage, even maintenance, your entire application or service might go offline.
Ouch, all your eggs in one very powerful, very expensive basket.
Exactly. So while it simplifies some things, it concentrates risk. This means you absolutely must have robust disaster recovery and potentially high availability measures in place, which ironically adds back some complexity and cost. You need backups, maybe a hot standby system.
Yeah.
It mitigates the risk, but it's a crucial consideration.
This really brings up the core question then. How do you decide? When is vertical scaling definitely the way to go, and when should you seriously consider scaling out or maybe a hybrid model? How do organizations navigate this decision?
It's a strategic decision, absolutely. It requires looking at several factors together: technical, business, organizational. It's rarely black and white. First off, analyze your workload characteristics. Is it intensely CPU bound? Does it need massive amounts of memory? Is ultra-low latency critical? If yes to those, vertical scaling is often a strong contender. Also, applications needing strong data consistency, like traditional databases, or those with simpler, maybe monolithic architectures often benefit most.
So, workloads hungry for raw power or low latency?
Generally, yes. Think high-frequency trading, big data analytics platforms running complex calculations, large in-memory databases. Second, consider organizational factors. Does your team have deep expertise in complex distributed systems? If not, vertical scaling might be easier to manage with existing skill sets. Also, if the priority is rapid implementation to meet an urgent capacity need with minimal architectural changes, scaling up is often faster initially. Third, those regulatory and compliance requirements we discussed. If you're in healthcare, finance, government, the simplified data locality and easier auditing of a vertically scaled system might be a major deciding factor, sometimes even overriding pure performance or cost arguments.
Right, compliance can force your hand sometimes.
It absolutely can. Fourth, budget and cost. This needs a careful look at total cost of ownership, TCO, over, say, 3 to 5 years. Vertical scaling might have a higher upfront hardware cost, but potentially lower operational costs due to its simplicity. Scaling out uses cheaper units, but the complexity of managing many nodes can increase operational expenses. You need to model both. Fifth, what are your growth projections? If you expect steady, predictable, moderate growth, vertical scaling can work well, you upgrade incrementally. But if you're anticipating explosive, unpredictable, or truly massive global growth, the near-infinite scalability of horizontal architectures might be necessary to handle those peaks and that sheer scale.
So predictable growth fits vertical better, unpredictable fits horizontal.
Often, yes. And finally, risk tolerance and availability needs. How much downtime can the application tolerate? If the answer is absolutely none, then even if vertical scaling offers performance benefits, you might need the inherent redundancy of a horizontally scaled architecture, or at least a robust high-availability setup for your vertically scaled system, like an active-passive pair. Many critical systems end up using hybrid approaches, maybe a powerful vertically scaled database cluster, fronted by a horizontally scaled, stateless web application layer. Best of both worlds.
So it's really a complex calculation. Performance versus complexity, cost versus scalability, risk versus simplicity, making those smart trade-offs based on the specific needs, not just a tech choice, but a real business strategy decision. Okay, so even if you've done that calculus and decided vertical scaling is the right path, it's not always smooth sailing, right? What are the common hurdles or problems organizations bump into when they actually try to implement and run these powerful systems, and how do they get past them?
You're absolutely right. Choosing the path is one thing. Navigating it successfully is another. There are definitely common pitfalls. A really frequent one is resource utilization inefficiency. It sounds counterintuitive, but organizations often buy these incredibly powerful, expensive machines and then don't fully use them. They over-provision out of caution or poor analysis. We see estimates that many vertically scaled systems run at only 40–60% utilization.
Wow, so half the expensive machine might be sitting idle.
Often, yes. Wasted capacity, wasted money. It usually stems from inadequate monitoring or just being too conservative during sizing. Another issue is performance bottlenecks within the scaled-up system. Just because the whole box is powerful doesn't mean it's perfectly balanced for your specific workload. You might have tons of CPU power but be bottlenecked by slow storage I/O or massive RAM, but the CPU is pegged at 100%. Identifying and resolving these internal bottlenecks is key.
So you still need to tune the balance of resources inside the big box.
Precisely. Then there are the downtime requirements for traditional scaling. While things like cloud resizing and in-place container scaling are improving this, historically, adding more RAM or a new CPU often meant taking the system offline for maintenance. That's a huge issue for critical 2047 applications. We also mentioned cost escalation, that point where getting the next 10% performance costs 50% more. Managing the budget and knowing when to stop scaling up and consider alternatives is a real challenge. And of course, that single point of failure risk always looms. Even with internal redundancies, the entire system is still one logical failure domain.
Okay, those are significant challenges. What about the more technical weeds or organizational hurdles?
Sure. Technical challenges include things like hardware compatibility, making sure new components work with the existing system board or chassis. Optimizing for NUMA memory architectures can be complex for application developers. Ensuring storage I/O can keep up with the faster CPUs is critical. Managing thermal output and power consumption in those dense racks is a real physical engineering challenge. And software licensing, often based on CPU cores, can get incredibly expensive on these highly cored machines. On the organizational side, you might face skills gaps needing people who really understand deep performance tuning for these large systems. There can be resistance to change from teams used to different approaches. Getting budget approval for the high upfront costs of premium hardware can be tough, and managing relationships with multiple specialized hardware and software vendors adds complexity.
That does sound like a fair bit to juggle, from heat management to vendor management. So given all that, what are the absolute must-do best practices? How do you mitigate these risks and actually make vertical scaling work smoothly and deliver on its promise?
Right, it comes down to planning, discipline, and using the right strategies. For risk management, especially that single point of failure, you absolutely need comprehensive backup and disaster recovery. That means automated, frequent backups, stored off-site or even geodiversely with regularly tested recovery procedures. You need redundancy, built-in redundant power supplies, RAID storage, multiple network interfaces. Implement robust monitoring and alerting on everything: CPU, RAM, disk I/O, network temperature, so you get notified before a small issue becomes a big outage. And engage in continuous capacity planning to stay ahead of resource needs.
So backups, redundancy, monitoring, planning, the fundamentals, but extra critical here.
Absolutely critical. Then for general best practices. First, establish performance baselines before you scale. Know where you started so you can measure the improvement accurately. Second, implement gradual scaling. Don't just jump to the biggest instance size. Scale up incrementally, measure the impact, optimize, then scale again if needed. This avoids overspending and helps find the sweet spot. Third, maintain thorough documentation. Keep track of configurations, changes, tuning steps, essential for troubleshooting and consistent management. Fourth, prioritize automation and orchestration. Use infrastructure as code, ISC tools, automated scaling policies, scripting. Reduce manual effort and errors. Fifth, conduct regular review and optimization cycles. Technology changes, workloads drift. Periodically review your setup, maybe quarterly, to ensure it's still efficient and cost-effective. Look for new bottlenecks or optimization opportunities. And finally, align with vendor roadmaps. Know what upgrades are coming for your hardware and software so you can plan ahead and leverage new features.
Okay, that makes a lot of sense. Baseline, scale gradually, document, automate, review regularly, and stay aligned with vendors. It's about being systematic and proactive. So it's clear that with careful planning, vertical scaling is a powerful tool. Looking ahead now, how is it evolving? What's next? Especially with AI becoming so pervasive, what's on the horizon for scaling up?
The future is actually really dynamic and exciting for vertical scaling. It's adapting and integrating with new technologies in fascinating ways. A huge area is AI integration into the scaling process itself. We're seeing AI-driven performance prediction and automated resource allocation. Imagine systems that learn your workload patterns and proactively scale resources up or down before you even hit a bottleneck, optimizing for both cost and performance automatically. Research suggests this AI-driven approach can boost resource utilization by 30–50%.
So AI managing the scaling of the systems running AI, that's kind of meta.
It is a bit, but it makes sense. We're also seeing innovation in advanced processor architectures. Beyond traditional x86 chips, we have ARM-based servers gaining ground for power efficiency. We have specialized AI accelerators like Google's TPUs. There's research into neuromorphic chips that mimic the brain. Even early quantum processors could eventually offer specialized vertical scaling for certain problem types. The landscape of what you scale up is diversifying. Memory and storage are evolving rapidly too. Things like storage class memory, like Optane, that blend RAM speed with storage persistence, are changing how applications can be designed. High bandwidth memory, HBM, integrated directly onto processor packages offers huge memory performance boosts. And we're seeing computational storage drives that can actually perform some processing on the data stored within them, reducing data movement.
Processing inside the storage drive. Wow.
Yeah, reducing that data movement bottleneck. Edge computing continues to drive demand for more powerful, vertically scaled systems deployed locally, especially with 5G enabling more sophisticated edge applications like autonomous vehicles or real-time industrial IoT. And as we mentioned, container platforms like Kubernetes making in-place vertical scaling smoother means it integrates better into modern, fast-moving development cycles. It removes a key friction point.
So smarter scaling with AI, new kinds of processors, faster memory and storage, more power at the edge, easier integration.
Yeah.
What about the market overall? Still expecting that strong growth?
Absolutely. The industry predictions point to continued strong growth, heading towards that nearly USD 600 billion vertical market software figure by 2035. Cloud platforms will keep adding more sophisticated, automated, and predictive vertical scaling features. And one trend that will likely become more prominent is sustainability. Choosing energy-efficient hardware, optimizing configurations for lower power consumption, managing the carbon footprint of these powerful systems that will become an increasingly important factor in vertical scaling decisions.
It really sounds like vertical scaling, far from being some dusty old concept, is right at the heart of where computing is headed. AI, edge, efficiency, it's constantly reinventing itself. Hashtag outro. What a fascinating deep dive that was. We've really seen that vertical scaling up, isn't just viable. It's strategically vital for so many modern challenges. It boosts performance significantly, often simplifying operations at the same time. Those performance numbers, 50 to 200%, typical improvements, are just incredible. And it's powering a market rocketing towards potentially $600 billion by 2035. That's serious business. And it's not just about brute force, is it? It's about smart targeted application, powering demanding AI and ML workloads, ensuring critical regulatory compliance, enabling real-time processing at the edge. Sure, it has its limits and trade-offs, like any tech, the single point of failure risk, the cost at the high end. But by understanding those, planning carefully, and following best practices, robust monitoring, disaster recovery, gradual scaling, organizations can really harness its power effectively, optimizing costs and boosting efficiency. It really shows how much you can achieve by going deep within a single system. So here's a thought to leave you with, something to chew on. With technology evolving so fast, AI optimizing systems on the fly, new processor types emerging, how might our whole idea of scaling change in the next decade? Will those lines between vertical and horizontal just completely blur? Will we end up with some kind of unified diagonal scaling as the standard? Or are we going to see totally new, even more specialized ways of scaling emerge that we can't even properly imagine right now? We really hope this deep dive gave you that shortcut to being well-informed, maybe sparked some new questions, and showed you just how relevant and dynamic the concept of scaling up truly is.